J1.8 is about here, I think. You're gonna have to just tell me if I'm wrong there. And then this would be the circle you would circumscribe here, a constant radius. This would be 0.1, where ZL is. You come through here, and this would be YL here, and this would be 0.422 lambda. And this is your second point here. This would be your first point. This is what it should look like, I'm sorry. Now you're gonna move, y'all follow me on this class? You're gonna move from this point here along this axis, along this trajectory, until you intersect the one circle. So this would be your third point, all right? And I'll get to the distances in a second. Y'all follow at least the thought. We're gonna have 1 plus J something. The reason it's 1 plus J something is because I asked the stub to be minimized, right? Now you know ahead of time, if this is a short circuit stub, its impedance is 0, but its admittance is infinite, even when normalized, right? So when you come in for the stub, you're going to be coming into this point, which is infinity, and when you go this way, this is all negative. Do y'all follow me on this class? So you want to make sure, because you're going to be adding negative values, would be the first values, that would be the shortest possible stub. And because of that, you want to make sure that we land here. We have 1 plus J something. We got to add a minus J something to get rid of it. Y'all follow me? I want to make sure. How many do on this one? Now, on the final, I could say something different, where I could say it's an open circuit stub, and then you'd want to hit this point. Y'all follow me? Because then you would want a negative J something to get rid of, because if it's an open circuit stub, it starts here, and the first values here are all positive on the ring. Y'all with me? Okay, getting back to this problem. Now you shoot a line through here, and you'll see that on the wavelengths towards generator point, I forgot if it's 0.178. Can somebody just tell me what that outer point is, wavelengths towards generator? Say again?
Sure, 196.
196? Somewhere in there, yeah. So this is 0.198 lambda. Now, this is the thing that you have to understand. You came from here, you went to here. When I move from here to here, that's at least a quarter wavelength, right? So I know it's more than a quarter wavelength that I'm going to be moving. And how much further? The actual distance I'm going to be moving for D through line is going to be this point, 0.198, minus that point. But that's a negative value, so we add half wavelength. Do y'all follow me in this class? Remember, you go to the point you're going to end up at, and you subtract the point you came from, not vice versa. Some people took 0.422 minus 0.198. That's the wrong answer. Do y'all follow me? You have to add that half wavelength. So then I add a half wavelength to this, and I think it's 0.275 or 278, something like that. Is that right? So it's 0.275 approximately lambda. And I gave people wiggle room there because I know the Smith chart is an inexact instrument, but that gets it down there. Now that is the length of the through line. Everybody with me? At this point right here, you had a value, that's a 0.3, a 1 plus J, and I believe it's 2.6. You can correct me if it's slightly off, but I think it's 2.6, isn't that right? All right, now you've got to get rid of that J 2.6, right? So you come in here, and this is where people made mistakes. And remember, what you're looking for is these outer lines right here that are intersecting the outer circle. And you're going to come down to where you see 2.6. It's really J 2.6, but there's a negative implied there because it's below the I call it the equator. It's at the bottom part. Y'all follow me on that? Take a look in your Smith charts. Y'all see this? Here's the mistake that was made. A lot of people went to the point where they're on this trajectory and the 2.6 interacted, so they had something real minus J 2.6. That's not the correct point. It's just at the very outer rim, J 2.6. Y'all follow me? Then you shoot a line through here, and then this distance is the distance of the stub. Now, this point right here is 0.25 lambda on wavelengths towards generator. This point, if you eyeball it, I want to say it's 0.31, approximately, maybe just slightly less than that. Can you all see it on your Smith chart? Make sure you can locate that point. Regardless if you got it right, make sure you know how to do this one. So this one here is 0.31, and that's on the wavelengths towards generator, which means now the stub length is going to be 0.31 minus 0.25, and you can call that approximately 0.6 lambda. I'm sorry, 0.06. Now, y'all follow me on that? There's one problem about this. I was hoping somebody would see it. No, I got no comment. There's one problem about that particular length. Can you think about it? How long does any kind of transmission line have to be in order for it to behave as a transmission line and not two pieces of wire? This is an inexact science, but.
Tenth of a wavelength?
Tenth of a wave, is that a tenth? No. So really, we're under that, but believe it or not, because there's not a hard, like it's all perfect behavior, it's transmission line, anything over a tenth, and then anything less than a tenth isn't. This is probably going to be okay, it'll work. It might need a little tweaking, but it's still of the order of a tenth of a wavelength. All right, now if it was like 100th of a wavelength, it ain't gonna work, for sure. But I'm just telling you that now. Usually you want a tenth of a wavelength or longer, okay? And I'll leave it like that. So are there any questions about this problem? There were a lot of funny things that I saw. Some people really didn't know what to do with any of this, but most of you at least had the first steps. Here, and the mess up usually came here or getting the stub length right because you had a wrong point here. That was the things that were the mistakes for me, okay? This is based on homework, by the way. I just took this off of homework. I think even these values are from the homework. Does anybody recall this is an exact homework problem? It may have been. It was. And I did that for a reason, to kind of make people a little more relaxed. First problem. Okay, next problem. So this is a spherically symmetric charge distribution. And they have, I give you the volume charge density as 10 to the minus 9 coulomb per meter squared over R, and the units are coulombs per meter squared, or meter cubed, pardon me, meter cubed. And this is true from 0, greater than or equal to R, less than or equal to A. And then the charge density is 0 for R greater than A. And I ask you to go ahead and use, really, to just find the D field in the two regions. Now, I don't remember if this is the exact homework problem. I know it's the exact same form. I think I changed the charge density. I think the one I gave you was a little different, but it's fundamentally a function of distance, radial distance. So now you start with Gauss's law. And for R less than or equal to A, greater than or equal to 0, go ahead and write down integral of B dot ds over a closed surface is integral of rho v dv over the volume. And this is just general. Start there. Always start there so you know what you're doing. Now, the integral of d dot ds, first, you all agree it's spherically symmetric, right? If it isn't, you can't do this. If it's spherically symmetric, d is only a function of radial distance, and it's in the radial direction. Do we all agree there? All right. If that's the case, then this integral is really the surface of a sphere of radius r times d of r, isn't it, right? And what's the surface of a sphere? 4 pi r squared times dr. I can write out the integration if you want me to, but it's not necessary at this point. We've done it so many times. Do you agree with it, everybody? That's equal to the integral of rho v, and I'll put the triple integral one time here. Rho v itself is 10 to the minus 9 over r. Then it's times dv, which is r squared sine theta d theta d phi dr. And here, theta goes from 0 to pi, phi goes from 0 to 2 pi, and r, technically you should do this, prime these coordinates, and then go from 0 to r. You all agree with this? I'm putting the full integration there. Y'all follow me on this, class? It's a differential volume, and I gave you that, in spherical coordinates. Then it's just multiplied by the charge density, and you have to integrate it up to the point r. So it's everything inside. Remember, with Gauss's law, this is all the charge inside a sphere of radius r. You all with me? So for this one, it's going to boil down to, I'm going to do this a little differently. The sine theta d theta integration is minus cosine theta, and I know when I evaluate that from 0 to pi, I get 2. You all remember doing that many times, right? Then when we integrate d phi from 0 to 2 pi, you get 2 pi. So the effect of that is 4 pi. And I've said that several times. You all remember that? So the sine of the phi and the theta integral will always give you that 4 pi, right? Now, with the r business, I've got an r here and an r here, so it's singular then, right? Just r. You all with me? Not r squared. When you integrate r dr, you get r squared over 2, correct, class? So now I've got r squared over 2, and it's times 10 to the minus 9th, and that's equal to 4 pi r squared dr. And the thing that you notice about this is the 4 pi surely cancels right off the bat, but so does the r squared. And you're left with a constant. D of r is 10 to the minus 9th over 2. And that's the way it's going to be for this region. That's absolutely true. Now, for the second region, now I'm outside where all that charge exists. I talked about it that way. Now all the charge is inside that region up to A, right? And I've got a radial distance greater than A. So I'm going to write it down here, but you all follow me what I've done. So now I get this. Same deal as before. This is 4 pi r squared dr. On this side, now it's all the charge, so we simply set the limits from 0 to A, not 0 to R, on the radial integral, right? So I just put it down here. It's still a triple integral if you want it that way. And it's the charge density, 10 to the minus 9 over R. And then it's R squared sine theta, d theta, d phi, dr. But now, R's got hard limits from 0 to A. Phi goes from 0 to 2 pi, and theta from 0 to pi. As before, it's the same exact form, only the limit on the R integration changes. Then when I take a look at this, the R's cancel once again, one of those. And I go ahead and do this integration, and I find now I'm going to get 4 pi times 10 to the minus 9th. Then I have r dr is r squared over 2 from 0 to A will be A squared over 2. And all this is equal to 4 pi r squared d of r. I'm just showing you the steps, right? Next, we can eliminate the 4 pi right away, correct, class? After that, depends how you want to cast it, but you can say now this is for r less than or equal to A. Then you can say d of r here is going to be equal to 10 to the minus 9th over 2, and then it's really A over R squared. And that would be in the AR direction, coulombs per meter squared. And this is for R greater than A. And that's how that problem's done. Do you remember this set of homework problem like this? Almost exactly like this? Sure, some heads, but yeah, this, when if you do the homework, you're really set for the test, because all these things are stripped from the homework. Modified, maybe the charge density or something like that, but there's nothing funny about this stuff. The first one is just, I don't even know if I modified anything on that problem, the first one. So please, I'm encouraging you to do the homework when assigned, keep up with it, and understand it. Yeah. But no question? Okay. All right. Next problem. And I might add, I almost always change either the permittivity, conductivity, or value of mu. You'll see that as a function of spatial coordinates in the different problems that I give. They're not exact, but they're so close that if you know how to do one, you know how to do all the classes of problems because the same principles apply. All right, next problem. Oh yeah, this is permittivity. So I need the capacitance per unit meter, and you have something, and this is just per unit meter, so L doesn't matter really. And you have an inner radius R1 and an outer radius R2. And then in between these things, you have some epsilon relative. It's equal to 1 over, it's R squared. Yeah, 1 over rho squared, pardon me, rho squared. 1 over rho squared. And remember, this is a cylindrically symmetric system, so this would be the axis of symmetry here. And rho is measured outward from the axis. You can put it vertical if you want, but you all follow me on this? So it's cylindrically symmetric. Now, if we're doing this problem and I'm looking for capacitance per meter, the way we've done it in the past, you could start with Gauss's law if you want, but usually what I do is these kind of problems, you all see that this is a cylindrically symmetric problem. It makes sense to assume charge right off the bat. Charge per meter, you all follow me? So I'm going to assume charge per meter, and I'll just put Q sub M. So that's so much charge per meter, and because this inner radius here, you would assume there's so much charge per meter on the inner radius. You could get the charge density, or the surface charge density if you want, but it doesn't buy you anything, right? Not when it comes to how we're going to do this. I know I assume charge, and if you wanted to, you could say, well, the integral of B dot ds over the closed surface is equal to the charge enclosed, right? You could do it this way. This is going to be 2 pi rho times length L times d rho is the charge enclosed, which is really Qm times L. The L's cancel, and you find that d rho on this one is just going to be the charge per meter over 2 pi rho A rho. So you can do it that way, but most people by this time know it's going to be just Q per meter over 2 pi rho. Do you all follow me on this, guys? Because it's cylindrical symmetry. How many understand it? All right. If you don't understand that, please go through and go through the Gauss's law problems, because we did a whole bunch of problems to try to, burn this thing in your brain. Don't cram on this stuff. Keep up, or else then you'll have big lapses in your understanding. But this was meant to be something that was sort of a template problem. We have that as D, so we started with Q, we get D equal to the charge per meter over 2 pi rho, A rho. Then after that we get E, and E is equal to D over epsilon. So now I take this D, Qm, right, over 2 pi rho times epsilon naught, and then this is gonna be divided by 1 over rho squared, right? Take a look, because I give you the epsilon relative is 1 over rho squared, correct, class? So it's 1 over rho squared down here. And one thing you can see is I'm left with a 1 over rho downstairs, which is really rho upstairs. This is the rho direction. So here I'm going to get qm over 2 pi epsilon naught, and then it's going to be times rho in the a rho direction. So that's the E field. Once I get the E field, I got to get V. So V in magnitude will be the integral from R1 to R2 of the E field, which is qm, right, over 2 pi epsilon naught rho a rho dot dl. In this case, it's just going to be d rho a rho. And if you didn't put the dot product and things like that, I winked it at this time. I wasn't a stickler for it, but I need to see, at least you understand you're doing an integral of the E field to get the voltage. Something that indicates you know what you're doing there. And here, it becomes simply qm over 2 pi epsilon. And then it's going to be rho squared over 2 from R1 to R2. So really, there's going to be another 2 down here. And then I get R2 squared minus R1 squared here. And that is the magnitude of the voltage. Remember, with capacitance, it's going to be a strict positive value. So if you get a negative sign, just take the absolute value. Do you remember me telling you this, guys? All right, now, what happens next over here? Now, I know I need capacitance, so that's Q over V, right? Just like the problems before, we've got V. And that becomes simply 1 over that whole thing with Q gone. So it's going to be 4 pi epsilon naught. And then it's R2 squared minus R1 squared. I'll make one comment. A lot of people just wrote down what the capacitance per meter is for cylindrical capacitor with constant epsilon. That does you absolutely no good, because it tells me you memorized one formula but didn't know how to solve a problem with a variable value of epsilon. You have to be able to do that, and because it's so important. And the problems you're going to get on the final exam especially are based on this. It's this kind of stuff. You have to understand the theory to get the answer. Just memorizing formulas will do you no good. Y'all follow me on that? Please make sure you hear me. They're not hard problems, but you have to understand how to go about it. So that's the capacitance, and if you go ahead and put down the values, you get 4 pi. Epsilon naught is 8.854 times 10 to the minus 12. And R2 was 3 centimeters, minus R1 was 1 centimeter. And that's going to be the capacitance per meter. And what is it? Anyone? I forgot. End of the line out. 192. Is that it? 1.39 nano, right? Or what?
139.
Nano. I'm sorry, 139. All right. And please realize, I don't remember what problem that's from, but that was the one I gave you for homework that I modified epsilon. I think for homework it was just 1 over rho. Take a look. I made epsilon 1 over rho squared for this one. Next. Oh yeah. Final one is a real simple Ampere's law problem. And for this one, two cylinders, conducting cylinders, you might say, that are interleaved. Inner radius, I'll call it A, outer radius B. And this is meant to be a transmission line. And what you end up having is, on the inner sleeve, you have a current I going up, which is 5 amps. And on the outer sleeve, it's returning. So it's just like a standard coax cable. Instead of just a thin, solid conductor, you have a hollow conductor. That's the whole idea of this thing. Same exact behavior as a transmission line. So for this one, I asked you to find the actual value of the H field for 3 regions. It's cylindrically symmetric. You can plainly see that. And because of that, you know you're going to use Ampere's law, and the integral of H dot dl over any line integral is equal to the actual current I enclosed by it. So for this one, if we start out and we say rho is less than A, greater than or equal to 0, less than or equal to this. Take a look at this. Then this path integral right here would be simply 2 pi rho h phi, and it would be equal to 0, and therefore h phi would be 0. And this would be true for this range of rho. Do y'all agree with that? There's nothing flowing in the center, so until you get outside where A is, you get 0 h. This is one of the 3 real important things you see. Now, for the second range, when we go between rho greater than A, or equal to A, less than or equal to B, then we have the integral of H dot dl around the closed loop is equal to I enclosed. Remember that current, that 5 amps, is uniformly distributed around the surface. So it's just I, it's just 5 amps here. And this is still 2 pi rho h phi, and therefore h phi is equal to I over 2 pi rho. You can put a phi direction, but I didn't even ask you for that. I'm just asking for a magnitude plot in a second. Y'all with me? So that's that range. Finally, the last part, when we're at a distance rho greater than B, still the integral of H dot dl around a closed loop is equal to the I enclosed. Here it is not twice I, right? Because remember, the same amount, if we take a surface right here, all the current that goes in this direction, once I'm outside that radius B, is really mitigated by the current going in that direction. Y'all follow me? That's a real important point. So that means the net current outside there is 0, and by the same token as the inner part, that means 2 pi rho h phi is 0, or h phi equals 0 outside that range. So then when you plot it, and I just asked for the magnitude of the plot, it looks like this. And this is magnitude of h phi. It's 0 until you hit here, and then it's going to come down like this. And this magnitude right here is going to be 5 over 2 pi. Inner radius is 2 centimeters, isn't it, class?
Yes.
And that's this magnitude. Now, if people didn't put that down as the exact value, you didn't get anything off. You've got basically full credit if you've drawn that schematic, had those equations correct to 0, then that, and the other one. And I looked for the plot to tell me if you knew what you were doing, because this is what I saw sometimes. Even though they had that, I'll see this. That's not the plot. Y'all follow me? Versus radial distance, that falls off as 1 over rho. That's the one thing you have to capture. All right. Do you have any specific questions about any of the problems? Okay. If you look back at your homework, you're gonna see each and every one of these things is basically a slightly modified homework problem. That's all they are. None of them come out of the blue. Right? But you do have to understand the concepts, and not just memorize formulas. Please don't do that. All right, so that's that part. Now number 4. We're in chapter 4. And in chapter 4, if you look in your books, this is all about magnetism. We just did, I didn't really beat it up, but we did Ampere's law, which is very important. Next thing, there's 2 things that come out next. One is, you know how when we did electrostatics, we did the integral of d dot ds was charge enclosed. That was the integral form, right, of Gauss's law. Then there was the differential form, which was divergence of d was the charge density. You all remember that? That was the relationship. Well, now we do the same thing for Ampere's law. As a matter of fact, let me put this down. The integral of d dot ds over closed surface is was really the charge enclosed. And you could put rho v dv over volume if it isn't in thin sheets, but that's the actual integral form of Gauss's law. And the differential form is divergence of d is equal to rho v. These two are the same in essence, the same amount of information. You can get this from this by doing an integration over volume. I'm not going to bother, but remember, that's the differential here. This is the integral. When we have Ampere's law, we have the integral of h dot dl around a closed loop is equal to the I enclosing that loop, or I penetrating the closed loop. Sometimes people will say it's equal to the integral of j dot ds over a surface, a planar surface, where the rim of that Gaussian loop it's the boundary. That's the integral form, but if you take curl of h, you get j. That's the differential form. So that's integral, that's differential. Just like there, that's Gauss, that's Ampere's. Differential, that's integral. Y'all follow me on this, class? Now, I don't spend a lot of time with this and this talking about it. It's self-evident, they're simple differential operations. And in the back of your book, the curl is given explicitly for all 3 coordinate systems that we use. If you look back there, you'll see it. So if I gave you h and I wanted j, the only thing you do was simply complete this mathematical operation. Y'all follow me on that? It is straightforward as it gets. I can give you an example, but I prefer you do some for homework just to prove it. And if I give you a quiz, know how to do that. I will provide the curls, all right? The curl for the how to do them in the different coordinate systems. Just know how to take derivatives, that's it. The only thing you need. Now, the next thing is, do you remember how back here in electrostatics, you had D is equal to epsilon E, right? That was a linkage type thing. It had to do with material parameter epsilon. You also had one other one. You had J is equal to sigma E, right? That's current density. That's electric field. That was conductivity. Do you all remember that? These are linking material parameters and field quantities. This being a current density, this a flux density. Well, over here, we're going to find that B is equal to mu H. Now, how many have seen that before in physics? B is mu H. Everybody should have if you've had physics. Mu is called permeability. Mu is actually the permeability. All right. The units are actually henries per meter. And mu typically is given as mu relative times mu naught. And mu naught is 4 pi times 10 to the minus 7 henries per meter. And mu relative has to do with how much better or worse any material is at storing magnetic energy. That's the way I put it. With epsilon, it's how much better or worse material is compared to free space in storing electrostatic energy. Now, I'm going to tell you this much. When you talk about values of mu, before I go down this road too far, here's what's really important: transformers. You all know what transformers are, right? Usually low frequency transformers are iron. They actually are laminated iron. They take iron, they cut it into very thin slices, and then they coat those with a shellac or some insulator, and they stack them. The reason is it minimizes what is called losses, eddy current losses, because when there's a magnetic field, time varying, in an actual iron core, it induces currents. Those currents can induce loss. What you want to do is limit the range these currents can move to limit the losses. Y'all hear of eddy currents? Did Irwin talk about this, or Gross? All right, well, he probably did a much better job than I can do in this class, but eddy current losses are horrifically bad with transformers. That's why you want to do everything in your power to minimize it. Now, the reason they use transformers, they have magnetic materials, is we're going to get to the analogy of circuits, but did you all have magnetic circuits when you were Gross? All right, good. Well, you know that magnetic reluctance is like electrical resistance. And in order to get a lot of flux, you would like minimal reluctance, which means you want high values of mu relative. Follow me? Downside is high values of mu relative, you have eddy current losses and things like that. So it's a trade-off, but you need that in order to really concentrate the flux and minimize, or really concentrate the amount of power that goes from the primary to the secondary in a transformer. Most of the time in your work, you assume the transformers are 100% efficient. Power in, power out. VI primary, VI secondary. In other words, that's not quite true. There are losses, and you do have to account for them. Now, what's the frequency of the wall outlets here? 60 hertz. What is it in Europe? Anybody know? 50. This is much better than my normal class. All right. What is it for space-based transformers on satellites? Anybody? Low frequency. 400 hertz. At least it was, unless they've changed it. All right. There's all these standards. All those low frequency things are great to work around iron core transformers that have high values of mu. However, air core transformers, the higher in frequency you get, it's less metallic, more, you might say, exotic materials. They go down, and there's a lot of reasons for it, but air core transformers become much less efficient. Did Gross talk about this or not? Any kind of transformers made with non-metal. Any cores like that? I'll talk a little bit about that. What I really wanted to mention is with this is a material constant, and for just about every practical application in your life, you're thinking transformers and mu, right? That's primarily it. Now in your book, it's going to talk about 3 types. There's diamagnetic, ferromagnetic, and paramagnetic materials. Don't worry about that. The only thing you care about is they're magnetic. You don't care about how come they're magnetic. And with a magnetic material, it's similar to a dielectric. I have to give this little speech, and I only have a minute or two. Y'all remember when I said if you have a dielectric, you have little dipoles, a positive and negative charge centers, and they rotate. Well, I say they align themselves. Y'all remember that? Well, when you have magnetic materials, you have little magnets, you might say, little chunks that are considered dipole magnets. There's one big difference, and they align themselves with the magnetic field, just like the dielectric will. But there's one big difference with magnetic materials than there is in electric. You see this here? That implies an electric charge. An electric charge, that's something that's actually observable, right? With magnetics, the divergence of B is 0. That's akin to the divergence of D. Y'all hear me on that? Now, if the divergence of B is 0, it implies the magnetic charge density is zero. There are no magnetic charges in the macroscopic world. How many know that? 1, 2. That's real important. And here's what, 3. Now, that's in the macroscopic world. However, you know what the CERN superconductor, super collider is in Europe? Anybody? It's where they basically have a gigantic circular, it's a cyclotron, and they slam particles into each other at super high rates of speed, and they see what comes on in a vapor chamber. It's kind of a clever way to observe. They do find singular magnetic charges that last for 10 to the minus 12, 10 to the minus 15 seconds, some insanely small time. So they can smash up these magnetic dipoles and get a magnetic monopole, singular magnetic charge. Go look up, it's smaller than quarks or charms. They're this dinky things. But they exist only for an instant that a physicist would only appreciate. Anyway, I don't. But in our world, the magnetic charge densities are 0. So please remember that, because you're going to hear people talk about goofy things in your life. And one is that there are magnetic charges. There's magnetic dipoles, not charges. They're always in pairs, plus and minus. I'll spend more time on that next time. And if you have questions about